So it's good afternoon, everyone. It's time to restart. Lunch was quite good, so people are taking a bit longer, maybe. Hello, Anne. Thank you so much for agreeing to present. And it's a shame that we couldn't have your company here too, but we totally understand, perhaps next year. So there is a small change of plans due to some difficulty getting this streaming going. So Anne is going to present remotely. She's in the US. And due to this necessity to make this work right now, we asked Anne to present before IGL. So sorry about IGL, and thank you, Anne, also for being flexible. So Anne is going to talk about imaging-graded data interpretation and analysis for earth science studies. So Ms. Ying-An Chen. And well, we met at UT Austin this summer, and I wasn't aware, to be honest, of Anne's work, but she has a lot of experience in SAR, and in SAR, as you know, we're very interested in this topic, in this work, and there will be other presentations in SAR here today. So Anne Chen has more than 15 years of experience in SAR and in SAR algorithm design for Earth systems science applications. In 2017, she joined the Department of Aerospace Engineering Mechanics at the University of Texas at Austin. And since 2018, she has also served as a faculty member by courtesy in the Department of Geological Sciences at UT Austin. She currently leads the radar interferometry group housed in the Center for Space Research, and her group focuses on the development of new satellites, and especially interferometric synthetic aperture radar in SAR techniques for studying natural and induced seismicity, groundwater resources, natural disasters, and permafrost hydrology and carbon storage. She's also a senior member of the IEEE. So, Anne, could you talk so we know that everything is working, and the floor is yours. Thank you.
Screen, so let me see if everyone can see it. Is there echo? May I start now? So I can share my screen now. Hello?
Please, there's sort of.
I cannot hear.
You can start, Annie.
Okay. All right. So let me get started. So good morning, everyone. This is morning time in Austin, and good afternoon. It's an honor to be here and share some of the radar stuff I know. And so this talk will be mostly on a brief introduction of how imaging radar works. And also I will showcase some of the application. As we see, the radar images are complex matrices, and so it's actually pretty easy to adopt a lot of our current Fortran code into Julia for future adoption. And so as a start, I would like to first talk about how imaging radar works. So this is what we call the synthetic aperture radar. So from the spaceborne synthetic radar, at a time one, the satellite will fly over an area of interest. And the imaging radar compared to the radar altimetry will look sideways. So there's a vertical, instead of looking directly downward and receive echo reflected directly at the nadir direction, we will look sideways. And instead, it will illuminate an area of interest that is showing in this swath of in yellow. And typically, depending on the antenna design, the swath is about tens of kilometers to about hundreds of kilometers. And that is why imaging radar can actually cover a huge area of interest with a single path. And periodically, the satellite will send out pulses that is traveled through what we call the radar line of sight direction. And at a slightly later time, and at every ground pixel, it will receive echoes reflected for the amplitude information and the phase information. And when we put these pixels together, and what we get is a synthetic aperture radar image. And the algorithm can achieve a wide coverage because the ground swath is quite wide. And also we can actually distinguish a ground pixel that is typically meters apart. And that's why it can have a very broad spatial coverage and also a very high spatial resolution. And so for the two pieces of information reflected from the ground pixel, and the very first one is the brightness of the pixel, that is corresponding to the amount of energy reflected from each ground pixel. So that's a grayscale image, and because it's high resolution, it looks kind of like a black and white optical image, but we will talk later in this tutorial how they are complementary to those optical imageries. And for the phase information, and because each of the ground pixel, meter level ground pixel, they have many scatters that is randomly distributed. And so if you're plotting the phase of the radar imagery, they look like just a random noise. So for a long time, people look at the SAR amplitude imagery, and which can be used if you have a multiple of them to track like the ground surface and also how it changed over time. For example, tracking glacier movement and so on, and also monitoring the urban expansion. And we'll talk a little bit more about various applications using the SAR amplitude image and later of this tutorial. And if we have another satellite path over the same area of interest at another time, or maybe the two is at the same time if you have two satellites, and we can acquire another image over the same area through a slightly different imaging geometry. Here, there is a constraint that is two satellites is not too far away, so that the line of sight angle is approximately the same. And if that holds true, which means typically these two satellites are maybe tens or hundreds meters apart, and And we could actually calculate the phase difference between the two acquisition at the same ground pixel A. And at this time, instead, you can start to see, instead of seeing those random phases, you start to have those very pretty fringes that looks like data. And that is what we call the techniques of interferometric synthetic aperture radar, or INSAR. So for those INSAR application, we're interested in the phase difference between the two SAR acquisitions. And so what are those fringes mean? So I'm going to talk, that's actually dependent on the SAR acquisition geometry. And so here we have a simplified geometry where S1 shows the location of satellite 1, and the S2 shows the location of satellite 2. And so the line of sight direction is from the satellite to ground pixel of interest. It turned out, and if we know the satellite location accurately, which is typically true for the modern satellite system, onboard navigation system, and we could use the phase difference of phi1 minus phi2 that recorded from the two satellite acquisition to infer the range difference R1 minus R2 through this geometry. And once we know the R1 minus R2, we can then infer the topographic height Z at the ground pixel A. And that is why INSAR, the very first INSAR application, when they were first developed in late 70s and 80s, was used to map surface topography. And now if we know the topography already, maybe from an existing data set, and we could actually, based on the satellite geometry, to calculate the topographic phase and subtract it from the phase difference phi1 minus phi2. And then what is left if the two, between these two SAR acquisitions, the ground pixel moved from A to A prime along the radar line of sight direction, we could use this phase difference phi1 minus phi2 minus phi topo to infer the small deformation that occurred at this ground pixel between the two SAR acquisition time. So here you can see the phase is linked to the surface deformation by a fraction of 4 pi divided by lambda, where lambda is the radar wavelength. And typically for X-band data, lambda equals 3 centimeter. For C-band, that's the commonly used radar wavelength, and lambda equals 6 centimeter. And for L-band, lambda equals 12 centimeter. And that is why INSAR is sensitive to centimeter to millimeter level surface deformation. So here is a chart of the available SAR data from recent satellite mission. And you can see we have those kind of satellite mission data available since the 1992. That's the launch of the ERS-1 mission. And so all those satellites was grouped by their wavelengths, L-band and the top, 24 centimeter, C-band in the middle, that's 6 centimeter, and X-band in the bottom, that is 3 centimeter. And later in those different applications, we can see that for surface topography mapping, and all of those bands are usable. And also, but for some of the interpretation for certain application, one particular band will be desirable. And another thing I would like to mention is most of those satellites was actually are actually open access. So anyone on the internet can register account and get those data. And so another key difference here is prior to 2010. So those are that's what we call those are early INSAR mission. And so this mission tends to have our larger revisit cycle of the same area of interest every 35 to 46 days. And also occasionally they have some like incoherent spatial coverage. So for example, some rural area may be visited less frequently. And also there are big data gaps occasionally. And that is the earlier INSAR mission prior to 2010. However, after 2010, and especially after the launch of the TerraSat X mission and the Sentinel-1A mission, so I would say Sentinel-1 mission A-B, and now the Sentinel-1C was just launched last year. So the launch of the Sentinel mission is a step change. So first, the data is openly available, free of cost. And what is more important is with this satellite constellation, and we now have satellite data at every single land pixel on the Earth every 12 days, in some area every 6 days. So from the jump from having one new acquisition every 46 days to every 6 days, it means you could form many interferogram pairs over the same area of interest. And if we're talking about big data analysis, you need a lot of data. So before, if you only have like SAR images, there's very limited computational tool we could use to mine data. So it's kind of depending on the luck if you have a good signal to noise ratio. But now, over the last 10 years, and with those newly available data, and it opened up a lot of the opportunities for big data analysis to mine signals that would otherwise unobservable. And that's why over the last 10 years, I've seen a strong growing interest in the community to learning SAR. And that means we will really need a better computational software tools to promote the use of INSAR and user-friendly tools over a broader community. Currently, I have been working on radar software development since I was a grad student at Stanford, and I was continually promoting those software development. Currently, a lot of those software are written in Fortran with a paralleled OpenMP parallelization, and I believe those kind of computing architecture, because a lot of the processing need to be done at every single pixel in those radar images, which are stored as complex matrices. I think there's a good potential to adopt those existing code and modernize it in Julia. So I look forward to collaborate with the community to move those user-friendly software forward. But for the rest of the talk, I would like to first showcase what we can do once we have these kind of tools and the data available. So radar in remote sensing application, people has been long known, they are very useful. So the very first thing I would like to know is there is a huge development in the last 10 years over the field of satellite geodesy. So not only we have a lot of the radar imageries, we also collected a lot of the high resolution optical imageries. So here I would like to briefly talk about the difference between the two and then give you an example. So firstly, I would say they're both usable, and in many cases they are complementary. So the radar energy scatter of the materials differently from the optical imagery. So that is why over the same area of interest, the optical image and the radar image would look so different. And certain features will be better notified in from one sensor versus the other. And when you have both imagery available, and all we care is to mining as much information as we can, and typically will provide a better discrimination of the surface feature. And the second, optical imagery is optical sensor is a passive sensor, and so the radar imagery is an active sensor. So the difference between these two is that when you have a digital camera, it doesn't come with its own transmitter, and it didn't send out any signals on its own. Well, instead, it's just to collect the photons, which require illumination source such as the sun. And instead, for the radar, it carries its own transmitter, sending out the pulses and receive the echoes. And that's why it works equally well in daytime and nighttime. And later on, we are also going to talk about and also the reason, and in a later slide, that also for the radar frequencies, it actually sees through clouds and precipitation easily, while the optical imagery, if there's a heavy cloud, all you see is the cloud. So it works well in those kind of severe weather conditions for radar imageries. And also, later on, we are not gonna talk about this, but for the SAR synthetic aperture radar works, there's a very surprising fact that we mentioned the SAR imagery can achieve very high resolution, sub-meter level to meter level resolution, and this is independent of the wavelength. So you could achieve this kind of wavelengths depending design a radar sensor using X-band sensor or L-band sensor, and also you could achieve this kind of resolution basically whether you're using airborne when you're closer to the target or spaceborne when you're far away from the target. So this is a intrinsic property for the SAR algorithm. And so those are some key difference. And here I want to show you an example of the optical imagery over the San Francisco Bay Area. And so you have this kind of data from Landsat, since several generations of Landsat data and a lot of the commercial satellite imagery, such as digital globe. And so what we can see here is that for the optical imagery, what you see is a colored image that contains maybe the texture of the information and the color of each pixel. And so what we can see here is this cross is a San Francisco airport, and also you can clearly identify some of the urban region and the vegetated region as well as the water surface. And here is our ERS SAR image over the same area of interest. And later on, we are going to talk about some from the first order physics principle, how to interpret this data. But for the first look of this image, and we can see it looks quite different from the optical imagery. And that's a good thing, because if they look the same, then we probably don't have need the SAR imageries here. So what we can see here is that this cross is the San Francisco runway actually appear really, really dark. And the ocean here looks fairly bright. And once you're going to those bay and those calm water looks fairly dark as well. And typically the city region, they have very bright scatters, and so they look pretty bright. And also along those rural area, and you see these lines along those ridges, and we are going to talk a little more about why this is the case. But here is what we see from those SAR imagery. And to properly interpret those SAR amplitude image, that requires us to go back to know how SAR, the radar acquisition works. So the amplitude image, typically what we see is a grayscale brightness of the radar image in terms of the normalized radar cross-section, or what we call the sigma zero, the backscatter. So to interpret how the sigma zero actually is going to be controls the received amount of energy, we need to go back to the radar equation. If you look at a radar book, usually that shows up in chapter 1, and depending on the system design, there are many different forms of the radar equation. However, they all kind of works more or less the same. So I'm picking up a simple expression here, and to give you a little bit more physics intuition of what is going on. So the radar equation essentially is a way to calculate the received signal to noise ratio from a pixel of interest. So the terms on the top is related with the amount of like energy, like from like the PT, GT, AR, A scat, sigma zero divided by 4 pi r squared. This term is what we receive the signal amplitude, and then the KTB is actually the thermal noise term. So the very first term, PT, is related with the transmitter's power. So radar carry out its own transmitter. So if you have a larger transmitter that emit a larger pulses, and you're going to receive a brighter signal. So that's and the G of T is the antenna gain. So usually when you're sending out pulses, you don't just send it out all over the space. You typically have a preferred direction you're looking at, and that's why you could concentrate energy in this area. And A of R is the size of your antenna. So a larger antenna typically means and you can broadcast your signal more efficiently. And A scat is your size of your scatter, and for the imaging radar case, that's the size of your pixel. And then the sigma zero term is the radar backscatter that we actually see in the previous image. And then for the bottom, there is a 4 pi r squared times the power of 2. So that basically says if you have the same radar system trying to get a return from a target, the further away you are, and the smaller the signal, the amplitude of that will be. And it decays pretty fast because you have a two-way travel, and so it goes with the r to the power of 4 term. So all of these terms are determined on how strong your signal will be. And it's very important to see that the PT, GT, AR, A-scat, and also this R-square term. And so those are known once you design your radar system and your imaging geometry, like how far away your radar will be from your target. And so those could be calibrated after you receive the signal. So what we can actually get is a sigma 0, which actually contains information about the property of the scattering surface and also the imaging geometry. And the last term, KT system and B, and so this B is the bandwidth of the signal, K is a constant, Boltzmann constant, and T system is the thermal temperature, so KTB is also a thermal noise term from the system, which could be actually measured before you deploy the satellite. And that's why we have this term, and everything else other than the sigma 0 is really with the radar signal itself. And also, I want to mention that based on our algorithm, typically once you design an imaging radar signal, the SNR is typically pretty high. So you're not going to worry about, like, once you get an image, it's also already usually pretty clear, and you would not think about the thermal noise would dominate. Usually that's kind of the design of the system design to make sure you actually have a sufficient SNR for the imaging radar system. You're talking about SNR to 10 to 100 or more. So that's usually not a problem. But once we receive the signal after the calibration, the radar amplitude information is basically, you can think about that as equivalent as the sigma 0 term. And so how do we interpret that? And turn out it has a coupling of two effects. And so the very first effect is the imaging geometry. And let's see how that is associated with the perceived brightness of a pixel. So the scattering phenomenon is typically depending on the incident angle I, and this is what and in most of the case, the incidence angle does not look equal to the look angle. And here I want to use a simple imaging geometry as a figure on the bottom, this two figure to illustrate the definition. So for the look angle, so if you can see my mouse cursor, the top image, this is theta here. So the point on the top is the satellite location, and we see the normal direction. So the look angle is how the imaging radar looks sideways, and so the illumination direction. So typically for a typical imaging radar system, the theta angle is typically around 25 degree to about 30 degree. And it's usually be kept consistent for point location of interest. And so the incidence angle, local incidence angle, depending on the look angle, but also it depending on the local slope angle. So for example, for a flat surface, and so this is the case on the leftmost region on the bottom image, this incidence angle I, so here the line is the surface, I would equals to theta. Right. However, if you have a little hill, for the hill facing the side that are facing the satellite, the incidence angle is typically going to be smaller than the local angle, and typically a smaller incidence angle. And for the hill slope that is facing away from the radar, and you are going to have a larger incidence angle I than the look angle. So that is the definition of this too. And in terms of the scattering property, it is depending on the incidence angle rather than the look angle. So for the same surface, and so if we plot a typical curve of how sigma 0, that's the radar backscatter, is changing versus the incidence angle, we will get a curve that looks like this kind of a decay. And what you can see here is that so the incidence angle increase and the brightness gonna decrease. And usually for a particular type of the material, you could actually also measure those kind of curve in lab. Or like for a field test, you could do some calibration and measure something like that, or by like survey the same area of interest with different like incidence angle. And so what it says is that if you're directly look downward, and you're going to get a really bright return, right? And so, however, as you look increase your incidence angle, the most of the energy going to scatter forward, and there's going to be little energy scattered back. And then because of that, in SAR, the SAR amplitude imagery gonna be very, very sensitive to local topography because as you just across those ridge lines, the incidence angle I gonna change from a very small one suddenly to a larger one. And that is why earlier when we see this San Francisco Bay Area, those ridge lines are very, very visible in the radar imagery, but it's not as visible in this optical imagery. And why is that? It's because if the optical imagery, they have a very, very short wavelengths compared to those microwave wavelengths, right? And the several order magnitude smaller. And for those kind of wavelengths, the sigma zero with the I pretty much looks like a flat line. And that is why we would say the SAR amplitude image is very, very sensitive to even a subtle change of the local topography. Perhaps on the Earth, we already know the topography. That is not doesn't really add any additional information, but those kind of SAR sensors are also on board on a lot of the planetary science mission, especially for survey Venus. So we're going to actually have 2 SAR mission that will be launched to acquire imagery over Venus in the next 10 years. And so with the thick atmosphere and the optical imagery would not be able to see through the atmosphere, but the SAR image will be able to see the condition on the surface. And if we don't know the topography, those kind of how the ridge lines orientation goes, that is very visible in those SAR imagery would be very, very useful for some geological interpretation. And here is an example on the Earth. And for a lot of the planetary science mission, what we usually do is to develop an analog to some of the things we can see on the Earth. So if we have a Venus mission, they're going to be very interested to study the volcanoes there. And so before the launch of the mission, we could use this Earth observing SAR mission to see what the data looks like over the volcano on the Earth. So here is a SAR imagery of the Kilauea caldera, Hawaii. And what you can see clearly is that for the slope that is facing the radar, and we, based on this imagery, we can immediately know the SAR flight direction is probably on the west side and looks sideways. And so flight direction here looks this way. And that's why the slope that is facing the radar would look very, very bright. And for the hill slope that is facing away from the radar will appear dark or even shadowing. So if you have really, really steep hills, the microwave will not be able to reach to the shadow region, and those areas would appear completely black. And another thing I would like to notice that compared to the optical imagery, the SAR imagery actually looks fairly speckly. And this is because even for the same surface, if you're acquiring data, for example, 10 times over the same pixel, you're not actually going to get the exact same amplitude return. In fact, the radar measurement itself is actually a statistic, actually a random sample from a statistic distribution. So we would say a particular pixel maybe tends to be brighter, but in certain acquisition, it can also get a dark one. And that's why this speckles itself is interesting because if you have a multiple SAR imagery and you could plot the amplitude distribution, and typically we say this is from actually a relay distribution based on those radar scattering theory, and those distribution, the shape, the mean, the variation of the amplitude over the same kind of area of interest actually also contain a lot of useful information as well. And if you would like to actually get rid of the speckle to see a more coherent optical imagery like a picture, usually you will need additional filtering as well. And now we know for the same type of surface how the brightness actually change with the incidence angle. And another thing is for different type of surface, those curve actually looks different. So so the first order, and here I'm showing you just those are based on the empirical relationship, many field tests. If you have a smooth surface, the curve like would look, you will get a really high amplitude return for small incidence angle, and this sigma, the amplitude would drop quickly as the incidence angle change. And then for rough signal, and your incidence angle when it's small, it won't be as bright as the smooth signal, because of the smooth surface. You could think about that's like a mirror-like surface, and a rough surface, it tends to have a lot of features like variation, rough, like small features on the ground, so they tend to scatter signals in all directions, so it won't be as bright if you're looking directly downward. However, the decay is a lot more slowly as your incidence angle change. And because the radar satellite typically is looking at a look angle of 30 degrees, and given the known topographic slope on the Earth, so for most, almost like all the cases for those imaging radar data, we are actually averaging typically for the incidence angle. The rough surface would looks very bright for those imaging radars mission compared to a smooth surface. And that itself allows us to do some land cover classification on the for example, for this particular image, this is a RadarSat C-band data. And what we can see here is that there is a very bright band of data that is the limestone surface, and all those darker area are the mud area, so that tend to be smoother. And if we look back, if we recall our older San Francisco area, those airport runway looks very dark, and that's actually true for all the airport runway globally. And that's the reason is that for airport, you really like to have a smooth surface for the airplane to take off. So they tend to surface to be really smooth, and that's why they look super dark. And also for those water surface, if it's in a very calm lake or in a bay, they are mirror-like on the surface. That's why those surface also looks very dark. And because of this property, those star imageries are often used to map flood, and because they tend to be a darker region once it's getting flooded. However, that's not always the case, because for the very rough surface, like the ocean on a windy day in that San Francisco image, the water surface can actually appear also very bright. So it's really the surface roughness that matters rather than whether it's water or no water. And also, this is outside of my expertise, but there is a lot of people would like to build a different scattering model to better interpret the received echo at a different condition. And so they have those forward model to simulate what the distribution of the amplitude you would get, and then they could use those forward model to compare with the actual measurement, maybe through an inverse problem, and to better understand the surface properties. So there are double bounds. Those are typically common in the city area. When you have tall buildings, so that's why the city actually appear very bright in many cases. And those double bounds can also shows up when you have a large tree trunk. So those wetland with trees in it, and even it is a water surface, because of those double bounds algorithm, and they actually can appear fairly bright as well. For those forest area, there are a lot of tree branches, leaves, so they're actually working on volumetric scattering of a tree. So in that way, it appear to consider it as like a very rough surface, and so that's why they tend to be bright as well. And also you could actually using those scattering over snow or glacier to better understand maybe the snow distribution, and also the density of the snow. And another thing I would like to also mention is that for some of the extremely dense vegetated area, the scattering from this area can be considered the roughest area on the Earth, because there are so many scatters from at different heights with different trees. And that's why when there's a very rough surface, if you're seeing those curve here, it equivalently when the roughness goes up, the sigma zero curve flatten out, which means in those areas, your received brightness of each pixel will no longer depending on the incidence angle. And that's actually one reason this Amazon forest was actually used to calibrate multiple SAR sensor, so that like when you have a different radar design, and you get some relatively amplitude brightness, and if you want to compare those signal data from different platforms, and those extremely rough surfaces is a good area for calibration. Lastly, we would like to talk a little more about the wavelength dependency of the black scatter. So here is a figure, and so basically when the radar wavelengths, and so we usually talk about the horizontal axis here is the particle size versus the wavelengths. So one means the particle sense that you're scattering the signal is equivalent to the radar wavelengths, and then the vertical axis is the scattering efficiency. And what we can see here is that you can really start to have a lot of the scattering going to happen. So when you reflect the signal away, like start to have those scattering rather than go directly through it, when the particle size is comparable to the radar wavelengths or larger. So when the particle are too small compared to the radar wavelengths, there's not going to be much scattering happening. This curve actually drops very quickly, and that's why the microwave just treat those particles as not there. And interestingly, and this is actually the reason that the radar can actually see through cloud, because for the microwave, those wavelengths is at the order of centimeters. And so these are actually comparable to the ice and the water droplets in this cloud, right? And so, but however, if you're talking about the optical sensor, so those optical wavelengths is much smaller than centimeters. They're several orders smaller, so those particles would appear to be much larger compared to the wavelengths, and that's why no scattering actually occur at the optical wavelengths, and you actually just the scattering. So the droplet are much smaller than the wavelengths, and so that's why no scattering occurs at this cloud, and it is directly see-through. But those droplets are large compared to the optical wavelengths, and that's why the scattering occurs, and the signal will not be able to penetrate. I'm sorry, I might mixed it up, but the sentence here and also from this plot shows that. So basically, you can only scatter when the particle size is larger than the wavelengths. And so also for the radar wavelengths, and that means because of the scattering efficiency occurs at a different size of the scatters. And so if you have a multi-band, sensor, so with X band, L band, and P band, and then you're acquiring data over the same area, and that allows you actually survey a different part of the forest region. For example, maybe there's a pine forest area, and if you're using X band lambda equals 3 centimeter, this wavelength is comparable to those leaves at the canopy top. And so once they reach there, scattering occur, and the waves those X-band signal will not be able to penetrate much deeper than the top of the canopy, and most of the return is coming from those leaves. However, if you're using C-band, that's a C-band, 6 centimeter, and you were able to actually go through to reflect the back a lot of the signal from a larger, like a scatter, which typically means the smaller branches on the trees. And the L band, and you're talking about the 24 to 27 centimeter, and that allows you to actually survey some, get energy reflected back from those major trunks, larger branches. And as you're going even further, you're really going to be directly penetrating more, and to see the surface and also the bigger scatters. And as an example, here is the two radar imageries are quite over Midwest in a lake area. And so from C-band, that is on the left, and L-band, 24 centimeter on the right. And we would like to mention that a tornado actually passed through this area and destroyed a lot of the forest roughly 10 years prior the acquisition of those imageries. And you can see most of this area, the lake appear really dark, and those brighter pixels are the forest area, but you could actually see a tornado scar that is marked in this L-band image that is not visible in the C-band image. And this is actually related with this scattering efficiency. It's because after the tornado actually destroyed all the trees in those paths, over 10 years, some smaller tree regrow. However, the time is not sufficient for them to get those bigger tree trunks, and but those smaller branches already there, and that's why from the C-band radar that this tornado path looks not different from the surrounding area because they have those leaves and smaller trunks. However, due to the lack of the major trunks, and you could still see a darker scar over this tornado path just because 10 years is not sufficient to grow those bigger trunks. That is where the L-band data is reflecting through. So that's kind of give you an idea why those multi-pass, multi-band SAR sensor are very important for survey forest area. And in fact, I think there's a large community trying to use those SAR return to estimate the global biomass, maybe from different portion of monitoring the vegetation health. And lastly, I would like to mention that for depending on the area, you have to know the dominant control for the brightness. For area like with agriculture, and so the brightness of your return for the same surface also greatly depending on the composition through the dielectric constant of the scattering medium. Or what I'm showing here, those are empirical model. Basically, you're controlled with a soil moisture sensor on the ground and also the backscatter signals. And so they derive those empirical relationships. So what it's saying here is that when you have a wetter soil, the surface tends to be brighter. And that's why if you're having the agriculture area, those sand measurement, because if the topography, the surface slope remain the same, and so you control that. And typically those agriculture areas are flat, right? And so, and after watering, and when the soil moisture is high, you can actually see a brighter return from these conditions, and that helps us to also monitoring the vital zone, the soil moisture there, and by building some forward model. And so people has been using those SAR amplitude image to solve for the actual soil moisture that is comparable to some of the in situ sensor. And the idea is if you were able to establish a relationship, you could scale up instead of have those localized sensor. You could perhaps getting a global map of the soil moisture and at a different time. So lastly, I just basically showcase some of the application for interpreting the amplitude image. For my own work, mostly I'm working on interpreting the phase difference between, you can just grab two SAR acquisition of the same area of interest using similar imaging geometry and calculate the phase difference. And so those phase difference was used to measure surface topography and surface motion. So here I'm showing the figure A, that's what we call an interferogram. And so what you can see for the first order is basically you get the two SAR imageries, you co-register them so they are aligned together, and then you calculate the phase difference, and this is what you get out of that. So in the ocean area, because the surface, the water surface, you don't those kind of algorithm doesn't work very well in the surface area because the surface changed too much, and it's not stable. And so, but in the land area, so this is Kilauea, Hawaii area, and you can see there's the first order, those fringes looks like those contour lines. And by walking through the satellite imaging geometry, how far away the two satellites is, you could actually translate those fringe lines into topographic height. So for example, in certain condition, perhaps each green to green that's corresponding to maybe 100-meter elevation change, something like that. So that's why INSAR can be used to measure the surface topography. And if we know the surface topography from the existing data, we could calculate the topographic fringes and remove them. And what is left here is a surface deformation that is happening at the Kilauea caldera and also the East Rift Zone. I have to say, this is the Hawaii's Big Island, and if you have been there, you might notice the image is upside down. So this is on the top is the south direction, and on the north is the north direction, and so the feature on the left bottom corner is a Mauna Loa, and here the feature here is Kilauea and the East Rift Zone. And so the reason the image is upside down is because those images were acquired in radar coordinates, because the satellite is in an ascending orbit, means it is flying from the south to the north. And so that's why the very first line of the image from the near range to far range is actually the southmost line. And so if we do that, the image would look like upside down. However, you could, the satellite like geometry, we can have additional step called geocoding to resample the image from the radar coordinates, which only the radar expert are familiar with, into the geographic coordinates along height, and so that's more comfortable with most of the other people to visualize that. And so what is interesting here is you can see in the Kilauea caldera area, there's a blue to red to blue kind of a color, and those are actually corresponding to some of the subsidence. That is, the Kilauea caldera was deflated during this two-star acquisition, and the magma, the lava was actually traveled to the east into the East Rift Zone, and then there's a dike intrusion that opened up the surface, and then they have some eruptions here near the Father's Day in 2007. And so those kind of signature are clearly visible in those in the ferrogram. And this is a L-band sensor, which means if you see green to green in those deformation map, that correlates to 12 centimeter of deformation in the radar line of sight. So line of sight direction, and so that's why you can see those small features. And so for mapping topography and the deformation, I would like to first commenting on mapping the DM, because most of those information launch was trying to map a surface deformation. So they're flying over the same area of interest at a different time, and then we would remove the topographic phase using an existing DEM. However, if you have a two-star acquisition, two satellites flying over the same area, right, and then the phase difference could be used to generate the DEM, because if you are acquiring data at the same time, there's no deformation, and the other noise term would look similar. And so in terms of using generating global DEM, which is actually having some emerging interest again, and we're talking about three major techniques. So the very first one is optical stereo instrumentation. So basically you have multiple optical imageries, and the acquisition geometry, and the same target would appear at a different location. By measuring this offset, you could reconstruct that same image and recover the DEM. And the same idea you could actually, using the radar imagery, the amplitude information, if they're acquired with a very different imaging geometry, combine them, can retrieve a DEM. So the problem for, of course, like this is actually commonly used given that there are so many optical imagery available. But a true global map is typically going to be difficult, because optical imagery is limited by cloud cover, and you can only get those imagery during the sunlight. And many of the area, actually 90% of time, is cloud covered. And so in those kind of area, you will not be able to use this kind of techniques to retrieve the DEM. And also even with, and usually in order to require like a DEM over without holes, you will need quite many things eventually to receive like cloud-free things. With a comparable imaging geometry to require DEM. And also the lightning condition doesn't mean when you have the sunlight, it's the same sunlight. The light intensity on a sunny day and a cloudy day is different. And that's why you will need a lot of the control point. So depending on the exact system, and we're talking about meter level resolution, and a vertical accuracy of 10 meters can be achieved. And but those require sustainable ground control. And because of those issues, a truly global coverage is unlikely. And also there's another technique called laser sensor. So basically, and it works similarly like those radar altimeter. You have a laser, you directly look downward, and you receive a reflection back in a short amount of time to measure the height. As you fly over an area, you get the height profile along that is 1D profile along the flight path. So those laser sensor has a very, very high vertical accuracy. We're talking about sub-meter accuracy. This is the best accuracy we can get over a larger area. And however, laser, they are limited by the same condition because they're at the visible wavelengths, right? And so noted by, so they're affected by the atmospheric cloud limitation, heavy weather, and also usually the laser sensor, they are carrying maybe several laser beam meters apart, and so each swath is less than 1 kilometer. And so because it's essentially, instead of having an image, it is a 1D profile. In order to have a global coverage, you will need many repetitive flight, which makes the global coverage feasible. However, those kind of setting can be useful if you're interested in a very localized area where a dense survey is possible. And also it will be useful if your area do not have a lot of changes. So for example, in the interior of the glacier, the DM doesn't change, it's relatively flat, the slope is small. So that in this kind of a case, you don't need many measurement in order to construct the height. And that's why there is a LiDAR mission called ISAT was launched to retrieve the DM. Mostly it's called ISAT because they're interested in those kind of a polar ice region. And for radar interferometry, because this is what we do, it's not limited by cloud coverage, and it can achieve a required resolution like meter level resolution, tens meter of resolution, and a meter level accuracy in a measurable red time. So that's why, to my opinion, this is actually a very ideal candidate. For example, SRTM mission was actually launched in 2000. This is a open access data many people are still using nowadays. You have a shuttle with a radar transmitter in the main shuttle. It has a receiver in the shuttle and another receiver on a metal rod 10 meters length, and another receiver that's from a baseline. So that's why you get two images at the same time from the two receiver, and then you can use that to acquire the data. The data acquisition over south 60 degrees south to 60 degrees north is only need 11 days with a 30-meter global resolution. So those kind of data can be acquired because each pass is tens of kilometers of swath, so can be acquired mapping the entire globe very efficiently. And a more modern one was a TandemX mission, is still in operational service, but the data is not openly available, is that you fly two radar satellite information and acquire data at the same time. This particular configuration, if you have good object control, can make the separation between these two satellites a little further. So the SRTM data, this length of the baseline is 10 meters, but for the SRTM data, this spatial separation is about 50 centimeters. And when you increase the baseline for mapping topography, it typically means a better accuracy of your deformation map. And in terms of surface deformation mapping, and if you already have a radar satellite, the same satellite that repeatedly visits the same area, maybe every 12 days, like the Sentinel mission, and we can map surface deformation. As an example, this is the very first interferogram that is published as a cover of the Nature shortly after the launch of the ERS mission, which captured the Landers earthquake in California in early, I think in 1992. So this image covers a 90 by 110 kilometer area from a single interferogram formed by one star acquisition before the earthquake and one star acquisition after the earthquake. And this black line shows the rupture of the fault. And the image actually captured this butterfly feature that people have been calculating using the crustal deformation theory. This is what we are supposed to see if there's an earthquake far field deformation field. And however, it is until the launch of this ERS-1 mission, people can actually measure the deformation of the Earth with such great detail. And such a shape of the butterfly image allow us to better construct the fault geometry, for example, the depth of the fault, the dipping angle, and the geometry better. And so another application and shows an earlier is recently, like in a lot of the active volcanoes, those INSAR data was actually regularly delivered to monitoring the volcanic activity and small deformation. So here what we are showing is another interferogram that capture a similar event near the Kilauea and also the East Rift Zone to show those underneath underground subsurface magma like migration from the Kilauea caldera to the East Rift Zone near the Pu'u area. And another, more recently, so when the SAR data was first launched, they were used to the solid earth application, mapping larger, like tens of centimeters of deformation from volcanic activity and large earthquake. As the data quality gets better, people start to be interested in centimeter to sub-centimeter signal, and many of them can be linked to like permafrost degradation or aquifer pumping. So people have been known surface subsiding. There's a picture before in SAR radar we do field survey, shows you the land elevation from 1925 to 1975 in 77 in Central Valley, California. And as surface water sometimes extended drought, people start to rely on confine the groundwater pumping. And so you start to see those kind of subsidence in all over the world around the aquifers. So here what we're showing here is the land subsidence in San Luis Valley, Colorado during the summer pumping season. And the figure B in blue is the uplift we show in the winter recharge season. And in this area, we could actually, using the well data to calibrate those INSAR image and turn those deformation map into the actual groundwater level. So what we are showing in the bottom, blue is the actual groundwater well measurement, and pink, red, and green are the groundwater measurement inferred from the INSAR satellite data. And we can see they're consistent, and the availability of those satellite data allows us not only to fill the temporal and the spatial gaps of the data and allows us to go look back in time. And also for the Colorado case, we can actually see because of the local groundwater management, in this case, the groundwater actually remains stable, and that's actually one of the law requirements for sustainable management. Last of the list, there are two additional examples. So these two examples actually involve both the phase information and the amplitude information. So the INSAR data has been used to derive the glacier velocity in Greenland and Antarctica in areas with fast-moving glacier. The fringes, so those fringes actually are good for capturing centimeter level of motions, maybe within 6 days, right? But for some of the faster motion moving glaciers, those fringes would be too dense and decorrelated. And in this case, you could actually use the SAR amplitude image and do the pixel tracking. You can do that with a radar image and optical image to locate the offset of the same feature over different images. By counting the satellite geometry, you could derive the velocity map for those areas. So both pixel tracking and phase measurement are used. So pixel tracking was used for larger motion, fast-moving glacier, landslide, and the INSAR phase measurement were using to measure much subtle deformation, centimeter to millimeter style. And lastly, earlier we mentioned the SAR images has been used for land cover classification, whether you have a water surface or maybe rough surface. And what we recently found is you're combining information you could retrieve from both amplitude information and the phase information, maybe some auxiliary DEM information. You could actually achieve a much better classification over like 9 different classes. This is an area for the Houston area. We were able to identify water, urban area, mixed urban, like suburban area, forest, and a different type of open natural area with different vegetation density. Such data will be useful, especially for coastal region, for stone search modeling, because of those different land cover types actually correlates to different roughness of the surface, and those roughness of the surface is a very important layer to be constructed for as input data for the stone search models, because very rough surface area effectively can slow the stone search, and that's another active area we are working on in our group. So that's it, and it's a great pleasure to share all those study research with everyone here, and I'm happy to take a couple questions if there's any.
Any questions? Any questions? No questions, and thank you so much. Oh, we have a question, Felix. One second, microphone is coming.
Hi. Yes, thanks for this introduction into SAR. In the beginning, you said you have some Fortran code that is for the processing of the data that you would like to convert to Julia. Could you elaborate on that a bit?
So let me clarify something. So there's several SAR users here. I can see 4 or 5 at the moment. Then there is also, I know of, so like work in the sense of data analysis, but also work in the sense of creation of tools, such, for example, SAR processing JL, a package that has been initiated. There's a lot of work to be done still. Can we hear you and now? Yeah. Oh, good. But and can you hear us? We cannot hear you now. Oh, I think she missed the connection. She's not here anymore. But so, obviously I cannot answer your question. But the whole reason why we invited Anne is exactly because of that. She is interested in working in Julia, and I told her that we were organizing this event. And she's interested in working with Julia in SAR, of course, but she has a lot of software that her group developed already. And one of the things they want to do is, in fact, convert or co-use some of the software they have in I think it's C and Fortran. And she has also PhD students. And so, yeah, it will be great to enlarge this pool of people who are contributing in SAR in Julia. That was the goal. So it's a shame the connection. I don't think she's in the call anymore, but we will be very happy to set up a meeting with all the INSAR users with her to make this bridge and see how we can move faster, hopefully. There's a lot of work to be done there. So in the meantime, I think Anne is back. Anne, can you hear us? Oops. Go on.
There's an open source, highly supported C package for all of the different SAR processing steps, and also the readers are a nightmare to write. And the Julia wrapper for the C package would negate all of the maintenance of maintaining the SAR processing cycle. So if you could just get the wrapper, Julia wrapper on ICE, that would be ICE 3. That would greatly accelerate this.
Yeah, good, thanks. I think we should talk about that, yeah, and definitely include also Anna in this loop, yeah. Thank you for that. even though rappers is not like the Julia way, it's probably the best way to start, at least in this case, for sure.
SAR processors can be gargantuan depending on what you want it to be.
Yeah.
I mean, this has a dev team of 10 people on it.
Yeah, exactly. Yeah, why not use that? Yeah. And I don't know if you can hear us. If you'd like to answer Felix's question. I guess you can hear us, or we certainly can hear you. So we're gonna move to the next presenter, but in the meantime, here, we keep the promise that we're gonna organize a meeting between the SAR people we have in the room and include you and as well to try to explore ideas on how to move faster on having more operational stuff in Julia for in SAR. Thank you, and so much.
So we will now move to the next presentation by Mr. Eigil Lippert, which is currently pursuing a PhD in numerical glaciology, in which he is working with the reconstruction of the Greenland ice sheet and its glaciers, going back to the last little age, ice age. This work is mostly centered around finite element modeling of glaciers and trying to understand their main drivers and dynamics. Before this, he did a master's degree in engineering, focused on Earth observation data, large-scale physics, and machine learning. He was involved in satellite observation and analysis and developed a method for synthesizing landslides in the INSAR coherence domain and building an algorithm that could detect these signatures in real-world SAR coherence data. He also developed an INSAR coherence processor in Julia, which could process CLC data and create interferograms and coherent estimates. He is currently in the process of porting this work into an open source library together with 3 other people.
Is it for this one? This one?
Yeah. You need this?
No.
No?
I haven't HDMI. Okay. Yep. All right. Hello. My name is Eigil, as was just said, and I'm a PhD student. I defend my thesis next month, and I've been working on this stuff, which is like modeling. Long-term can mean different things, but in my context, it means modeling from the Little Ice Age, which is the end of the 1800s to today. And I've specifically focused on this glacier, which is in East Greenland. I'll show you a map in a second. I'll talk a little bit about, I'll just do the overview. So I'll give you a bit of background first of this idea and what I've been working on, some of the modeling basics within the field. Then I'll just discuss the baseline model that I developed, and then how it can kind of, I think it serves as a good kind of small example of why it's nice to move to Julia. And yes, so basically it's going to be a small like case study of using Julia to take advantage of auto-differentiation to solve some physical modeling issues. All right. So the interest area is shown on your right, so that's Eastern Greenland, and it shows the whole basin of this specific glacier. It's one of the glaciers that are kind of pretty important in terms of the total discharge, at least in the last 20 or 30 years. It has been a big contributor to sea level rise, which is also the kind of reason why ice modeling is interesting. And particularly, I've been looking into how to model and reconstruct this glacier in the past 100 years approximately, since the end of the Little Ice Age. And that's interesting because a lot of modeling studies are mainly looking at the past few decades. And since we're interested often in 100 years projections, some of the dynamics and interesting dynamics of modeling are like kind of, it's hard to really investigate and understand what's going on a longer time scale when we base the models on a short, like when we parameterize the models based on a shorter time scale, basically. So that's the idea. Yep. So the reason why it's possible to do this is actually because these guys, they flew around over Greenland in the beginning of the last century. So around in the 1930s, they flew around and took pictures. The guy in the middle, Lauge Koch, was responsible for these missions, and he was a geologist and was interested in rock formations and stuff like that. There was also like a dispute with Norway at the time, who was settling kind of illegally in Greenland. And so they were also monitoring a little bit that nobody was living there without permission. Oh, but anyways, these pictures are then enabling us to get information about the past geometry of the ice. So let's see if I can use my mouse. Yeah, I don't know if you can see it, but this orange arrow is pointing to the so-called trim lines, which are lines you can still see in present-day imagery. So this is an image from 2013, and this is from 1933. And you can see the ice has thinned out, and this gives us some information about the thickness of the glacier back then. This is a glacier called Fenris Glacier. And also we get some information about how much the glacier has retreated based on this front migration data. So this information can kind of help us get an initial state for the geometry of the ice. Also, to those of you who doesn't know already, ice can be modeled as a fluid, and you can kind of get hints of why this is the case, because you can already see here in these black lines that it looks like kind of it's flowing. And so on longer time scales, like decades and so on, and even longer, it kind of behaves like a fluid. And this is some kind of small, I just took all the Landsat imagery from the 80s going forward. They're not geocoded correctly in the first part, but they'll stabilize around the end of the 80s. But I just wanted to, it's just because you'll get like the feeling of this flowing ice. Once it stabilizes a bit, it's easy to see. So now you can start to see that it's really flowing kind of into the ocean. So just to give you an idea of what's, so up here is basically the ice sheet and the interior of Greenland, the ice sheet, and then out here is the ocean, and the ice is flowing out like this. Yes. All right, so some basics for the modeling. Basically, we take the Navier-Stokes equations and then we neglect momentum advection and inertia, and based on something called the power law relation, a power law relation called the Glen's flow law, we can then connect stress to strain, and that enables us basically. That's kind of the very rough outlines for ice modeling. More schematically, what is going on is that when snow accumulates and with time becomes like ice, then if you get enough mass, basically, it will start flowing under its own gravity, and it will flow, roughly speaking, like this. So it will flow from the middle and out to the edges due to deformation from gravity. And you can both have land-terminating glaciers, as you see in mountains, and also some places in Greenland, and then these ocean-terminating ones. I've mainly been working with the ocean-terminating glaciers since they're pretty interesting. They're much more dynamic, and they're both influenced by the ocean as well as the atmosphere and what's going on under the ice sheet. And here's the stress balance equations for for the ice in its full form. So in order to model, we would like to reduce them a little bit to make it a little bit more easy. And we do so by this so-called shallow shelf approximation, which is where you kind of only consider the horizontal stresses. So you treat it as a kind of membrane. So all of this is considering the stresses on a like infinitesimal ice cube inside the ice. And since the glacier is much wider than it's deep, then you can kind of ignore, the idea is you can ignore the vertical components, and you end up with these equations. They are now reduced from this to this. And you can use if we use the last equation in the z direction, we can solve for p and insert it into the other equations. And so we end up with only two equations. And that's the shallow shelf approximation. And we can kind of image it as a kind of giant membrane that we pull or stretch, or like a sheet of paper or like a sheet of something, yeah. So that's pretty common to use this approximation in ice modeling, especially if we do larger scale modeling, because it's computational a little bit more manageable. All right. Yes. Okay, so the next thing is that, so here's another schematic of an ice shelf, of a glacier. And the glacier consists, when it's like ocean terminating, it sometimes have this ice shelf, which is basically that the ice separates from the bedrock, and then it becomes floating, and the ice moves out this way, and then it breaks off and can become icebergs. And we have this kind of some of the interesting kind of points of interest is the grounding line, like where this separation happens. That's a very active point of research. And there's also a lot of research going into when the ice will break off. So like what's happening at the ice front. And then we have like the major forcing close to the ice front would be the ocean currents. Yes, so that's what this schematic shows. But the thing is that in the shallow shelf approximation, we actually assumed that we were working only with an ice shelf. But often ice is grounded, meaning it actually has some kind of friction with the bedrock. There's something opposing the flow, which would not be the case if it was floating. Additionally, it turns out that if we only model the ice with deformation only, then we can actually not reproduce the observed velocities. So somebody came up with the idea of introducing a proxy term, or like an ad hoc friction term. So you introduce this basal stress term that can modify the equations basically, and it's often modeled like this. So it's some coefficient that's dependent on the basal velocities. All right, so the reason why I've told you all this is because this term is, first of all, pretty important in modeling, and secondly, we don't really, there's a lot of active research going on figuring out how to do this better, and it plays a big role in future projections. So some of the overview of what I've been working with, but also the idea behind, I'm going to show you some Julia work in the end. But basically, we use this shallow shelf approximation, and then we model it with a final element model software that's called the Ice Sheet Sea Level System Model. It's pretty well known within the field and has been developed in 2010. It's a C++ program that is operated either through MATLAB or Python usually, and it has different capabilities. One of them is that they implemented inverse problems to calibrate some of these parameters inherent in the program, which is pretty useful. Based on surface velocities, you can then calibrate the friction so it matches what we observe. It also has this capability of adapting the element size to the observed velocities. And then there are several different friction laws implemented, and these friction laws are there are a lot of different ones. This is actually not the most realistic one, but it's pretty easy to get it to work for examples. And also in my work, it turned out to be the most stable one in terms of actually doing some modeling. It consists, so this is the basal stress, sorry, and this coefficient is what you would invert for. It's just a coefficient. This is the effective stress at the bottom of the glacier, and then you have the basal velocities and some exponents. So in my work, what I had to do was I wanted to reconstruct the model, and in order to set up the model, you need to have initial conditions. So we got the geometry from the images I showed you earlier, but we still need the basal friction or the conditions underneath the ice. In order to do that, I solved the inverse problem for present-day data, because present-day data we have surface velocities. You can see down here is a velocity magnitude map of Kangerlussuaq Glacier, and you can see it goes from almost 0, and within how much is that? Like within like 50 kilometers, it increases to be like around 10,000 meters per year. So it's a quite huge like change in the magnitude scale. But then we can invert for friction coefficient in this based on these velocities, and then since I don't have velocities in 1933, then we assume that it's constant and that this friction coefficient doesn't change over time. And then we can use the geometries to initialize the model, run it forward in time based on surface mass balance models. So these are atmospheric forcings, and then changes in the front position. So this is also some kind of forcing. It's just where the front is, basically. We can compute the misfit and then use that to either inform updates of this process or to inform just the misfit in general, which I also did in the paper that I released on this work. So one of the huge issues with this work, or what I really struggled a lot with to get to work, was that since I have no observed velocities, as I just mentioned, I cannot invert for friction coefficient in the past. At least not in a kind of not in the methods I had available at the time. But I still had to take care of this area of the domain, which is now ocean, but it used to be ice covered. So basically I don't have any friction here, but I need some friction for the model to work. What I did was basically this is an extrapolation problem, and I need to figure out how to solve this somehow. So first, it might seem like it's like a small area compared to the total area, and might not be that difficult. But since there's no ice immediately around it, and because of the structure of the flow, and since all the ice for the past 100 years has to pass over this area, this friction in this area is super, super important, and it's very sensitive to what happens here. So what I ended up doing was I did like a correlation based extrapolation where I correlated the bedrock topography to this friction coefficient in the known area, and then I used that to extrapolate, and by tuning it a little bit, I got it to sort of work, having both realistic initial velocities, but also not having like a major ice mass build up over time. So it was like a trade-off between having like a plug in the end or like having a very big slide. So neither is very nice because they're not producing present-day results that are realistic. But it was pretty annoying. This process was not so satisfactory from my own point of view. It's a lot of tuning, and it doesn't, like, it worked, and it has like the misfit, present-day misfit was acceptable, but it was not like the best. And here you can see the actual friction coefficient field that I've extrapolated. And you can see it's kind of, you would say, some kind of average with this small bedrock signal in the middle. It's slightly darker. I don't know if you can see it, but it's slightly darker in the middle. And yeah, it kind of worked. But this process, especially if this was to be more generalizable and repeated for other glaciers, it would be very interesting to figure out a better way to do this. And this kind of is bringing me to automatic differentiation in a second. So I just wanted to mention that I tried various different of these friction laws, and the one I ended up using was the only one that worked. It involved a lot of tuning, And I also tried these spinning up methods and trying to correct the initial geometry and stuff. I tried a lot of stuff to make it work. So yes, so now we'll go to the Julia part. So it's pretty. So this work is mainly done by so far by Cheng Gong and Matthew Mogliam at Dartmouth College. They have been working on porting the original source code to Julia, but it also means that it has like a C++ or MATLAB like syntax still. It's pretty one-to-one. I think so. As far as I know, so I was, I wanted to present this here, but it's mainly their work. And I think the reason for this was to ease the transition from existing users of ISSM, since it's quite a, there's a lot of users of this software, and also to make sure that things are working like for the right reasons. Yes, so it's still pretty early stage. So like we've managed to get stress balance solving to work, what I showed you in the beginning, and then also running transient solutions, so running the model in time. It uses Enzyme for the automatic differentiation, and then I will just now go through 2 simple tutorials that I also uploaded on the JuliaEO site. Here we are. So if you're interested, maybe I should zoom in a little bit. So a bit more. So if you're interested, it's and you want to install the package, it's at the registry. Just at the moment, there's apparently a bug. I think they're waiting to get fixed in Enzyme. So you need to add the hashtag main to get the main channel from the registry. Otherwise, it won't work. Right. Talk through it, because running it will not provide so much more information. And this is the main object in the program. It's a model object, and it has all of these properties like a mesh and a geometry, ice geometry, and mask, blah 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 blah. And all of these can then be updated and set to something specific. Initially, so this first tutorial is just creating a square ice shelf. It's pretty basic, but gives a nice idea of what we need as a minimum requirement to actually model the ice with the final element solver. So we set up a final element mesh using this triangle method, which takes in a model object and then the domain name and the resolution you want. So you can see you input like these EXP files, which in this case is just some square with some size, and you give the resolution of 50 kilometers. And then you have the set mask function, which will inform where you have floating and where you have grounded ice. And it has this keyword called all that just sets everything to floating. So it gives you this mesh, which has where all the nodes are floating. And then we can start setting up the geometry of the ice, and we define the thickness to be just a function of y, having like a max and a minimum thickness. Boom, boom, and we get like this. So if we go back, so it will be its thickest down in this end, and it's thinner out in this end. And it kind of resembles, that's just to show you why it sort of makes sense. So you can see it kind of resembles the outer part, the floating part of an ice shelf, where it's thicker in the beginning and it gets thinner as we get closer to the ice front or the Earth's ice terminus. Initially, additionally, we can also we have to define the base. So that's the base of the glacier, what's underneath it, and we do it based on the hydrostatic equilibrium. So it looks like this, and we get then the result looks like this. And again, it's kind of resembling this schematic. You have like more submerged ice when it gets thicker, and when you get further to the thinner part, it's less. So yeah, it looks like that. And then finally, you can define the ice surface by just adding them together. Then we want to make sure that the bedrock, so this is the bedrock, that it's not touching the base, so we subtract some meters basically. And then we'll start up setting the initial conditions and the boundary conditions in a second. Yeah. So the initial conditions are we're just gonna set the velocities to 0 in both directions. And then there's a small recap of what I already told you. So this is the shelf stream approximations, or the shallow shelf approximations in tensor form. And here you have the tensor expression, or the tensor written out. And then we have this Glenn's flow law that I actually didn't include in my slides. It's written out like this, where we have some exponent and this prefactor, which is determined experimentally. So it's usually just set to some constant that you can find in some tables. It's temperature dependent, and it's set here. So we set those two things up, like the exponent and the prefactor. And then we have we use this Bot's friction law that I told you about before. We set P and Q to 1, and the rest is already given. And here the friction coefficient actually doesn't matter. I think it's more the code doesn't ignore this thing, despite the fact that all the nodes are floating. So there is actually no effective friction in this context, in this example. But there will be in the next one. Then finally, we have to set the boundary conditions, and we do so by saying that the top of the domain is the calving front or the ice front. So that will have like Neumann conditions, and then the surroundings will have Dirichlet conditions. And that's what we set up here. So we find these vertices that are on the top boundary, and then after that we set the Dirichlet conditions by doing the same thing essentially. So this SPC is the velocity on the boundaries basically. Then we set some numerical tolerances, and then we can solve the model using the solve function, and we tell it to solve the stress balance. It runs for a while, and then we can then plot the velocity solutions. So this is the velocity of this kind of theoretical ice shelf, where we can see that closer to the thick part of the glacier, or the ice shelf, sorry, it's slower, and then it speeds up as we go towards the terminus. Yep, and then I will just go through this other example where we tried to use some AD to investigate the sensitivity of the model basically. So there's some imports, and then instead of setting up all the geometry stuff and all that again, we import a model from one of the MATLAB versions that is already, like this model has already been set up with all the geometry. It just saves us some time. It complains a little bit because there's some additional things that hasn't been implemented yet, which I implemented in the original, which I implemented in the ISSM version, the MATLAB version. And then we can look at the friction field. So this is the friction coefficient that results from doing an inversion in a real life setting. So it has like higher friction in these areas where the ice is kind of not moving. Maybe I should just show you this. And this is the resulting velocity. This is the observed velocities actually. So you have, this is the Pine Island Glacier in Antarctica. It's a quite important glacier, and it has like a pretty big floating part here in the end, and then it becomes grounded around here. And when you use the observed velocities to infer the friction coefficient, you get something that looks like this. The resolution is a bit coarse, which I think is just to speed up this tutorial basically. It could be much finer. Yes, then we solve the forward model to get model velocities, and it's just equivalent to what we just did before we saw in the square ice shelf case. And then we can plot that. It looks like this, so it's slightly different than the observed, but it's kind of close enough. And then we get to the sensitivity analysis. And here we use enzyme, and then we've defined like the cost function like this. But instead of using observed velocities, which could also be interesting, in this tutorial we just set it to 0 to investigate where the modeled velocities are most sensitive to the friction coefficient, basically. So we're interested in this gradient dJdC, which is the gradient of the cost function with respect to the friction coefficient. So we'll get some idea about where the friction coefficient will mean most for the modeled velocities. Yes, and I think we'll hear more about this AD stuff tomorrow if some of you don't know what it is, but basically we can then propagate the gradient back to the input and see how sensitive different input parameters are, like the output is to the input, basically, and use it for many other interesting things. So this is defined like this. We tell it what the independent variable is, and then because of this legacy one-to-one porting, there is also you need to support, give it kind of information about you give like some string keywords about what you're interested in. So in this case, the friction coefficient, and that you use this specific cost function. And then we solve it, and this time it's because we've set this is control to 1, it knows that it has to solve like the inverse problem or the AD problem. Like solve it as with automatic differentiation. And when it's finished running, we can then look at the gradient. So this is the JDC. And so to me, I thought it was an interesting small comment or like confirmation about what I found in a lot of my own work that took a long time, was basically that the model is really sensitive. Like the friction coefficient choice really affects the modeled velocity a lot, very close to this grounding line and close to the front in the main trunk of the glacier. So you can see this is kind of where the transition is if we do like a simple approximation of the grounding line. So that's really where the friction coefficient plays the largest role, which is kind of just emphasizing the point that the reason like this area is just super important, and it's important to increase our understanding of the friction in these areas. Yes, so far we can also repeat this work for the rheology, this B parameter, to kind of figure out where it's most sensitive. And we could also set up the problem differently and try to estimate or update the friction estimates that we already have based on observations. What I hope to do myself next is, first of all, I would like to start contributing more to this package, first of all. And secondly, let me just go down. I have this, I wanted to try and experiment with introducing, instead of using these friction laws, then instead like proposing a model that can give you the basal stress directly. And to do that, I was thinking to use some kind of neural network in this physics-informed setup. And the nice thing is that now I can use the ICE model from deduce, and I can differentiate it, so I can actually get the gradients to update a like hypothetical basal stress model that would be able to infer some basal stress instead of using known or like these friction laws. It would be very interesting, I think. So that is all from me. Yes, thank you. Yes, Alex.
Super impressive.
Thanks.
How difficult was it to implement enzyme? Like, did you have to structure your code in a friendly way that enzyme was able to interpret, or is it like fully automated? Doesn't matter what you throw at it.
So I was a little bit on the side during this process because I was finishing up my PhD, but I know from Chengong that they had some troubles actually because they wanted to use the analytical adjoint that they already knew. They wanted to use that instead of getting it from enzyme, and that was actually a bit tricky. It took some time for that to work out, but I worked closely with one of the guys from the enzyme team to make it work. So it took a bit of effort, I think, as far as I understand. Yeah. Is that, yeah, yeah. But I'll talk to him after this actually, so I can ask for some more details and come back to you. Yeah. Yeah, it's a good question. To me, as I think it seems like a bit of an aside from my point of view. As you know, they're interested, but I think they still need to prove that it has enough. How can you say, like, it will benefit them so much that because you know there's always a challenge of being able to answer interesting research questions in order to qualify. Actually, spending a lot of time on working on it, and since a lot of ice modeling is kind of only 10 years old, like numerical ice modeling, there's still a lot of interesting questions to answer with normal numerical ice modeling, is, you know, the stuff that's already working. So, but my own hope is that they will spend more time. I think they're also interested. I mean, the community is super great, right? And the language is amazing. So it's something at least I would also like to push. So. Mm. Yeah. 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 Yes, and also I think so. Actually, there's been a little bit more. It has had a bit more momentum for the past half a year, but I think when they started out, they really quickly hit this roadblock with the enzyme stuff. So, but now they managed to get over it, and it's going a bit quicker now. Yeah. Cool. Thanks. That's it, I think.
Thank you, Mr. Eigel. Now we have up next a presentation by Mr. Alex Gardner, who is a research scientist in GPL Sea Level and Ice Group. He studies the Earth's cryosphere with a particular focus on glaciers and ice sheets and their impacts on sea level rise and water resources. He's most interested in how glaciers respond to natural and human-induced forcing and the implications for our future. Alex is a member of NASA's ICET-2, NASA GRACE Surface Topography and Vegetation, Surface Deformation and Change, and Sea Level Change science teams. He's also involved with many novel initiatives to measure ice on Earth and elsewhere, including the use of snake-like robots, eels to look for life under Encelada's icy shell. Alex is also the primary investigator of the It's Live NASA Measures initiative.
Okay, awesome. It's great to go right after a presentation on ice because I can skip a bunch of the stuff that I was going to do to orient you to ice and why it's important. I would love to see a community that's supporting an ice sheet model. So, I mean, keep at it, man. That'd be really cool. There's lots of great questions. There's lots of unknowns. There's some great problems. Some of the best problems in earth science have to do with the Antarctic and the Greenland ice sheets, and I'm going to convince you of that in a minute, but this part here, well, let's see, where am I going to walk over to? Pine Island and Thwaites. This part right here, you just saw in the last presentation. It's on the edge of collapse, and there's these irreversible feedbacks that happen on ice sheets that could cause like multi-millennial feedbacks where you'll lose the whole West Antarctic ice sheet over long periods of time. And that's happening with Greenland as well. And so we're kind of like right at the threshold. We don't know if it's like 1.5 degrees or 3 degrees at which we cross that threshold. And so the type of research with these models that's really trying to get at that question of when do we cross that threshold is pretty fascinating. Okay, so who am I? I'm still trying to figure that out. A presentation mode would be great, wouldn't it? Yeah. All right. I don't want any of these. Sorry, it's giving me things on my end. I am a research scientist. I love technology. I came from earth science, but then I kind of fell in love with the engineering part of it. I did an engineering undergrad, and just generally really curious. But where I sit at NASA is I kind of sit from top to bottom. So I sit like on the missions and trying to think about how we implement the missions and what they're going to measure, why they're going to measure it, with what accuracy, but then also, you know, the software, and then deriving understanding from all this information that we're collecting. And I've been increasingly interested in Julia and what Julia can offer, because we just have this infinite amount of data, and it's no longer the data that's limiting our ability to generate knowledge. It used to be, 10 years ago, you just wanted more data so you could answer more questions. But now we have so much data, we just can't access, manipulate, process the data to kind of generate the understanding. So the kind of next revolution in earth science is really being able to master the data. And I think Julia can play a role in that. I work on all sorts of different missions. So GRACE is one that measures Earth's gravity. I work on ISAT-2, which is a photon counting laser altimeter. And so kind of the technologies that are being used are novel and really fascinating. So ISAT-2, in a single micro pulse of a laser, will shoot out, 5 to 7 trillion photons, and they go down to the Earth and they scatter, and about 6 of those photons will come back to the telescope. And so you're now at the point where you can take, the smallest quanti of energy and actually measure use it to measure the distance to the surface of the Earth. So just absolutely fascinating thing. GRACE is a satellite that measures changes in Earth's gravity, and the primary cause of changes in Earth gravity is the movement of water around the planet. And so you just send up 2 satellites, and they're orbiting the Earth in a free orbit, and you have 2 satellites that are trailing each other, and you're just looking at like fractions of a hair difference in the orbits between those 2 satellites, which allows you to map the geoid. You do that multiple times, and you can see the change in the geoid over time and how mass is moving around the planet. And then NISAR. So we have INSAR, this NISAR mission in collaboration with ISRO, with the Indian Space Agency, is going to launch in April, and it is going to be absolutely fascinating. It's going to showcase NASA's ability to do kind of next generation INSAR from space. And the amount of data flowing down is going to be infinite. So we had to build new downlink stations just for this satellite because there's going to be so much data. And this is officially NASA's first kind of cloud-hosted data set. And so kind of the way we work with the data is going to change quite radically. And it's going to take us years to be able to figure out how to really master this new paradigm. I propose missions, none selected yet, but I also, at really low frequency radar, you can actually see through kilometers of ice, and you can map the bedrock below the ice. And so I've been pushing for a mission like that for a while. I'll keep pushing for it. I do science, I manage science. I'm sensor agnostic, and I like ice as a topic because it has great questions to answer, but really I'm just kind of interested in any good question. But I get paid because I know the cryosphere, so I better keep doing that. About 3 years ago, I got interested in Julia, and I really kind of locked onto the syntax. I really just like the syntax of Julia. And I've kind of remained, and I want to see this ecosystem grow and evolve so that other people can enjoy it, but also so that we can just accelerate the rate at which we're generating knowledge from all of this data. I think Julia really has a role to play in that. I've transitioned all of my research code over to Julia, but production code is another issue. It's still not mature enough, not supported enough to do production code. So all of our production code is primarily in Python and all the derivatives. But I hope we can change that. In fact, kind of in the next 2 years, I hope we can start generating some production Julia code. I am JuliaEO's power user. That's what I would classify myself as. I bother the developers that put in all the work and just keep asking for more. And sometimes they ignore me, but sometimes they come and help me out every once in a while. And I'm humbled by the JuliaEO community. It's just a fun community to be a part of. Nobody's getting paid. Everybody's here just purely out of passion. So I just tried to generalize like what it is that we do in Earth observing, and I think this captures most of it. This was in response to some LinkedIn post where some expert in the area tried to tell us what it was that the process of generating knowledge from data, and I think he kind of got it wrong. And I think this is about as simple as you can distill it. Is you just have huge amounts of data, you have huge amounts of data from satellites, but then you have all this other ancillary information that you need to correlate, group, subset, whatever you use it for. And then you're really spending all of your time in I/O. I/O is a huge issue, and Shul covered that really well. I/O is still an issue that we're trying to solve. It hasn't been solved yet, but there's new technologies and there's convergence in those technologies within the last year that are making us really excited about what that could be. So instead of thinking of files, you'll think of data sets, and so a data set will just be a URL, and then you'll be kind of navigating that space as some giant array of data. And so you're not doing all of this file management, you're abstracting away dimensionality of the data. You can abstract all of that away because that's the first 6 months of like every PhD is just trying to get and organize and work with the data. So I'm hoping that those technologies will be adopted. So in any kind of EO project, you read in the data and then you quickly realize that it's not truth. It's not coming from like a weather model or a climate model where you look at a variable and you take that variable as some truth from the model. All of the data comes with high amounts of noise. And really the progress is in being able to filter out the noise and generate some sort of meaningful conclusion from the data. And then typically you have some sort of EO model. You're using that in some sort of calibration process, as we just saw. Tons of visualization, tons of iteration, because it takes kind of that domain expert to be able to make an advancement. And that domain expert understands how to look at the data. And we saw this with Martin looking at elevation. He knows how to look at elevation in every way so that he can quickly spot where it's not right. I think to someone outside of the field, elevation is just elevation, it's just a height. But then when you start looking at how we generate new understanding from it, you need to understand the data at such a deep level that you have to build that intuition to actually make any sort of progress. And then that's output to results. So I'm going to follow something like this. I'm just going to give an example of what I've been working on for the last couple of years to show how we're using the GeoJulia and other ecosystems to generate knowledge from this data. So the science question I'm going to answer, try and answer with this work is really how much have the glaciers responded to changes in climate over the last 20 years since we've had kind of the sensors that can measure the specific glaciers that I'm interested in. And I'm going to just walk you through what that process looked like, what tools I'm using, and so kind of what it involves to really make an advancement using this ecosystem, which is still fairly new. Ice is lost primarily through two ways. One is surface runoff, right? So you just melt the surface and it runs off into the ocean. But ice is a viscoelastic material, so it's also flowing constantly to the ocean, and it calves off, and so that's another form of loss. Those losses are happening all the time. You know, they happen since the dawn of time, right? Even if glaciers are growing, they're still losing mass because of water running off, and they're still losing mass because of ice calving into the ocean. But what happens when you change the climate is you go from kind of an equilibrium geometric configuration of the ice sheet to something that then has to find a new equilibrium, and so the geometry of the ice starts to change over time. And so when your inputs don't equal your outputs, you have a deficit and you have mass loss. And so the world right now is in a period where the climate is out of balance with the configuration of the glaciers. All the glaciers are now responding, trying to find a new equilibrium, and they're just dumping huge amounts of water into the ocean as they try and shrink their geometry so they can be stable in the current climate. We live on a fairly unique planet. It's right at the transition point between frozen water and liquid water. That's not the same for all other planets, and so when you change the thermostat just a little bit, you get just these disproportionate changes in Earth's cryosphere, Earth's ice. And so this is just what it looked like when it was about 4 degrees C colder 12,000 years ago, when you had the Laurentide ice sheet kind of covered all of North America and pushed out into Boston and created the peninsula. And this is the little piece of trivia that I always like to add, is this Laurentide ice sheet still exists today. It's right here, that white spot right there. It's been renamed the Barnes Ice Cap, but that ice is the same ice as the Laurentide ice sheet, so it still exists. And actually, that's the birthplace of the Laurentide ice sheet. So about 20,000 years ago, the precipitation increased, the temperatures reduced, and it started to accumulate on that Baffin Island there where I was pointing to. And then it grew out from there and covered all of North America. So a little piece of trivia. So when you look at the Earth's gravity and you look at its change through time, so the trend in gravity, you see these hot spots that pop out. This is with the solid Earth signal removed, so there's no glacial isostatic rebound in this signal. But this is what the trend in, essentially the trend in gravity looks like. And you see these red spots and these blue spots. And when you look at those, all of the red spots, and actually pretty much all the blue spots, that's all where ice exists. And so the largest contributor to changes in terrestrial water storage over time is just change in ice. And this actually affects the rate at which the Earth rotates. As you lose ice at the poles and you throw it down towards the equator, right, it starts to slow the rotation of the Earth and actually becomes a measurable phenomena. There are a couple locations, I don't know if you can see my mouse. Oh, you can, okay. This here is an inland sea that is losing water, and this is Lake Victoria, which is gaining water. And then this red spot here is actually groundwater pumping in India with a little bit of contribution from glaciers. And then you can see this ringing here, that is earthquake. And out here is another earthquake. And so you can see where those things have happened, but primarily it's just changes in ice. Here we see that there's been a change in the precipitation patterns in East Antarctic where you're getting accumulation. And then this here is called the Cam ice stream. It's an ice stream that was flowing fast a few hundred years ago and then just kind of came to a dead stop. And now you can actually see this thing starting to increase in elevation. But the point being that glaciers play a large role in modulating where water is stored on the planet. And because of that, it dominates the sea level change signal. So about 2/3 of all sea level rise is just from changes in ice. And then there's a smaller component that comes from thermal expansion. So if you warm ocean water, it becomes just slightly less dense, so it occupies more volume. And so that causes the sea level to rise as well. And then there's a small part from anthropogenic changes in land water storage. So if you build dams, you hold more water back. Those dams start to fill with sediment and they start to put the water back into the ocean, and you get that land water contribution. And then glaciers also augment river flow. And I'm going to convince you by the end of this, it can actually be to a very large degree. Even though they'll be, like spatially a small part of the landscape, there can be conditions where you have a dry summer month and the only place water can come from is the melting of glaciers. And so during kind of those critical periods where you have low river runoff, glaciers can be a large contributor. And then this is just going back to the tipping points that I was mentioning, is that we're really sitting on the precipice of irreversible changes in both Greenland and the Antarctic. So in Greenland, as you melt the ice, it starts to lower in elevation. And as it's lowering in elevation, right, because of the atmospheric lapse rate, it's actually getting into a warmer climate. And eventually you can turn the thermostat back, but the ice sheet will continue to waste away regardless of what we do. We are most likely crossed the threshold for that, or at the threshold for Greenland. And then the Antarctic is more uncertain, because in the Antarctic it has to do with these more complex dynamics that we're still trying to understand through the models that we just saw. So I'm going to talk about changes in elevation. The presentations today have been great to line this up. So we can also infer changes in glacier mass by looking at changes in elevation. It's not directly a one-to-one mapping, because the density of ice is also changing at the same time where you're gaining or losing mass. So that kind of complicates the issue, but you can look at these longer records here. This is with all of the satellite records combined. And you can see this is that hotspot area that we're just talking about here. Let's see if I can pause this. This is the Pine Island Thwaites area. So this is that highly active region that we're watching very closely and trying to understand whether we're crossing that threshold or not. This is that CAM ice stream. And so some of the patterns that you saw in the gravity also line up with the altimetry. But altimetry provides you a different observation. It's very high spatial resolution, whereas gravity is a very coarse resolution. From a meaningful orbit, you can only resolve the gravity to about 300 kilometer spatial resolution. So I'm gonna, with the exercise that I've been working on, is I've been trying to quantify the changes in all of the ice outside of Greenland and Antarctica. I actually consider those ones relatively easy to measure because the properties of the ice are not that challenging. It's kind of smooth and it's all co-located, but then you have all of this other ice that's in the mountain regions in Alaska and the Alps and Russian Arctic, Canadian Arctic, down in Patagonia, that contain a lot of ice, but they're kind of mixed with the mountain, and you got confounding signals, and it's a bit more challenging to extract that signal. So the instruments that we can use to measure glacier change are ASTER, which is photogrammetry. Gives us a long record all the way from 2000 to present. Has very high noise relative to other sensors, but there's a lot of meaningful information in there, and there's a lot of data, so you can beat down the noise if you work hard enough. We have ISAT-1, which was the first laser altimeter in space. That was from 2003 to 2009. It had a single beam and a 70-meter footprint on the ground. And then ISAT-2 launched in 2018. That's that photon counting laser altimeter that I was talking about, and it's got a very narrow footprint. It's only about 12 meters on the ground, and it's got 6 beams. And then there's the JEDI instrument, which is on the ISS. It's mounted on one of the instrument bays. It's an amazing instrument, but putting an instrument on the ISS comes with a whole bunch of problems. It's got jitter. It's not a free-flying mission. But it's got very good density, a lot of power. Because it's on the ISS, you can shove a lot of power through the lasers, which helps beat down the noise. And then we also have models where we can model the thing that we're trying to observe. And that's really the best world you want to live in, is because you have these either short spatial or short temporal samples of something that you're interested in. And then you want to fill in the missing information or the missing variables with some sort of model. And you want to constrain that to the observations that you collect. So this is the plan. You've got all this different input data. You got your climate data from ERA5. You've got your ancillary data. It's 2 terabytes, and then you got these repeat elevation observations. So JEDI is a 80 terabyte data set. ISAT-2 is a 14 terabyte data set. You got ASTER. It's another 400 gigs, and ISAT is relatively small at 130. So it's a big data problem. Not the biggest that I've worked on, but it's still a lot of data. And managing that data, structuring the data so you have rapid access to it, that's kind of the first 3 to 6 months of a project, is just setting it all up so that you can access that data. So reading in all that data, in this project I've come up with a tiling scheme because the data is so heterogeneous, and it's structured from the point of view of a mission operator. So one One example in particular is either ICESat-2 or JEDI, where they have their data as orbits, right? So it's like half an orbit. And so, there's no machine learning that you want to apply on orbits. You want to apply those spatially localized. And in order to do that with the raw data, you would have to just read in gargantuan amounts of data and then extract the part that you want, because the data was never structured correctly. And so in this workflow, I actually have to kind of re-chunk and retile everything to make it efficient. And then, so you have that data, and then you need to reduce it even further, so it's something that you can apply meaningful algorithms on. Otherwise, you'll be stuck in that first phase forever. And so you go through this data reduction, which is, you're masking the data, you're applying corrections, you're doing tons of filtering, and then you're doing some sort of data reduction, and then. So now you kind of have this cleaned up data set. You're still working with the raw data, but you've hopefully filtered out most of the garbage and applied the corrections that you need to. But then you need to reduce that further, so then you're doing a bunch of parametric model fitting, and you're doing gap fitting for various reasons. And then once you get to that point, you have kind of a reduced data set that you feel has very high accuracy, and then you can feed that into the model calibration. And as an example, I always like to remind people kind of the accuracies that we need to work with. So if you have an error of 1 centimeter per year in the Antarctic ice sheet, that will either double or halve your total estimate of mass change, right? So you're just obsessing about these very small errors. So when you fly these instruments over and you get elevation and you're within a meter, that's fantastic. Like that's kind of trivial. But when you fly these instruments over and then you want to look at the change, and that change is on the order of a centimeter, you really have to start thinking about the errors in all of this data. I wasn't talking to Martin when I said trivial. There's a ton of work in generating that data that you were working on. I'm just saying I'm working on the differences, not the absolutes. And the differences are a challenge. So then you have a model, and then you can calibrate your model to the observations. And that's because when you're in a mountainous region, any estimate of your climate is a wild guess at best, right? You might be able to get the deltas, like the change in time, but mountain climate is an area of active research and will be an area of active research for the next 50 years. It's like the last frontier. It's incredibly difficult to do. And so you have to have some sort of healthy balance between what can climate forcing give me, what do the observations allow me to constrain even better, and then how can I use that to calibrate the model. And eventually we should be able to invert for the climate. That's the hope of these types of things, is you should be able to invert for accumulated precipitation in mountainous regions, which would be even a better study than the one I've done, but more challenging. Yeah. You treat it as a relative observation. And so actually when I run a model of a glacier, I do it for like essentially an infinite number of elevation and precipitation classes. And so I always assume that whatever climate forcing I'm getting is wrong, but that it has some meaningful information in its variability in time. Because no model provides a good estimate in mountainous regions. There's no way you can run a forward model and believe it in a mountainous region. You can use it to infer things, but not as a direct. Yeah, so it is limiting, absolutely. Yeah. No, it's this. Yeah, it's in the model that I'm running. There's something called precipitation. You can run your model for various classes, and so I'm not. It doesn't have anything to do with ERA5. it's a way, some people refer to it as like sub-pixel downscaling, right? So imagine you have an ERA 5 grid cell, which is 32 kilometers by 32 kilometers, and then you were to run your model as though it was at a specific elevation within that range. You could also run the same, or I should probably describe this offline because it will take me a while to describe it. But yeah, it's multiple elevation classes. It's something they've done in CESM, and other models. Essentially, I'm running multiple versions of the glacier model on the order of 500 different instantiations of the model. And then I'm using the observations to determine which model instantiation was the correct one by minimizing the residuals to the observations. And then I feed that into downscaling. So this is kind of done on a 2 degree by 2 degree tile, and then you can downscale it to the specific glacier. You can then route that through the streams, and you can look at how much water is going into the streams from this glacier runoff over time. And then on the other side, you can kind of look at the larger aggregates for each of the regions, and you can figure out how much of this water is going into the ocean and contributing to sea level change. So that was the plan, right? It's just a couple boxes. And I still don't fully understand why it should take this much. I can describe it on this slide, but it's 50 plus packages and 10,000 lines of code. And I'm sure somebody could write it in 5,000. 3,000, maybe even 3,000 lines of code. But there is just a huge amount of, using a large number of different packages for all the various steps that are required. I bolded the ones that I use the most often, that are most critical to the work. And I'll talk about some of those coming up here. You've heard a bunch of these. So tools for reading the data, that's like, if we can't read in the data, there's no point continuing. So a lot of work in the initial years of Julia was just getting the readers for all this geospatial data, and that was work that was with no love, but done by people that were really committed to make sure that it happened. And then at the highest level, there's these 2 packages, rosters, which is absolutely fantastic, and Space LiDAR, which is also a great package. And I'm going to talk about Space LiDAR because I feel like rosters has already been covered in this. But I just wanted to mention Space LiDAR. So, this data from laser altimeters, it's very unique. It's not an image. And so a lot of the space data it's a roster. And all of the tooling is set up for these rosters. And then there's one sensor that decides to measure things in these profiles that are not spaced evenly along track, or it's just kind of messy point data, and a lot of it. And then the different missions have different formats and different metadata and different ways to access the data. And so Martin put together this absolutely incredible package that makes it as easy as, I want this sensor over this location at this time, and it returns the file names, and then you say, oh, I just want to go get those file names, and it will just download it. And it's fantastic because then it will also check whether you have the file or don't have the file. And anyway, huge amount of work went into that, and it's really valuable for people to be able to go and explore this data. So that's a shout out to Space LiDAR. Through the process of trying to do this, I also created a number of packages for things that I didn't have access to. So one that is still heavily under construction is this surface model of glaciers, right? So it's a 1D column model with all of the physics of how water moves through the ice, and how ice compacts, and all the things you need to be able to go from an elevation measurement to some geophysical meaning. GeoTiles is the scheme I came up with for how to partition things. I found that I was continually trying to partition things into a tile on Earth, and I just made some easy helper functions so you could just quickly query the data that you wanted and be able to go find it. And then bin statistics is one I'm actually going to show here because I use it kind of in everything, and there might be something else out there that exists, but I haven't found it yet. So I'm going to demo bin statistics. Better make sure I'm on time here. What's my cutoff time? So bin statistics is just a histogramming function for multiple dimensions, but then your histogramming can be anything you want to throw at it. So if you just have a bunch of point data and you want to reduce it by bins and apply some function to it, that can be a very expensive process because your data might not be sorted, and then you have to group it into these different bins and then apply the function. And if you're doing that with multiple functions, you don't want to be grouping the data multiple times, but then you also don't want to retain the original data after a while because it's going to be overbloated. So this bin statistics, it exports a single function called bin stats. And the function call looks like this. You put in a data frame. You specify what is your axis columns. So what axes are you going to do the binning on? And then for those axes columns, what are the edges of the bins that you're going to apply to those columns? And then you have what column do you want to bin on? So what column do you want to apply your function to after it's binned? And then you have a group function. So this can be applied just at the grouping level. You want to do a count of how many points are within a group. And then this column function is what operation do you want to actually apply on the raw data. And then you have an option to retain missing bins. And this can be really valuable because if you want every single bin to be returned, regardless of whether it has data, you want to have that capability. So I'm just going to show you what that looks like. So I just create some synthetic data here, and I'm just going to go to the visuals because I think that's really all you need to see. So here's a visual of kind of the raw data on the left, right? You have this scatter of data and it has a large degree of noise, and you want to reduce the data somehow. So in this case, we're just going to bin it. So we're binning it by 0.1 here, all the way out to 20. And we're going to bin the variable v2, which was defined above. And our axis that we're going to be doing the binning on is this x-axis, and so we're just going to put it into this bin stats function. And so on the left, you can see when the data gets reduced, I'm just showing that there's a coherent pattern under the data, but the point being that this data gets just quickly binned into this. I think that functionality is easy to replicate in other packages. It would just be a group by in data frames, yeah. Yeah. So there's one Python package that does this, and we're 2 to 10x faster depending on what the request is. I think it's in pandas. You can do it, but you can't do it in Julia yet, except with this. So then you have a bit more of a complex example. So you want to bin on x, but now you want to apply an operation to 2 variables. So now you're going to apply it to v1 and v2, and the default algorithm that applies is just mean. And so I'm not specifying any column function here, so it's just taking the mean. So in this case, you have 2 variables, v1 and v2. That's yellow and blue, and then you apply the bin stats function, and it reduces the data, and you get the result on the right there. Now you can start to get a little bit fancier, right? So you just want to bin along a single axis. You're just going to do a range from 0 to 20, stepping by 0.1. And now you're just going to apply a function to just the variable v1, but you want the mean, the median, and the standard deviation, right? So when it does the group and it creates the group, you want to apply 3 different functions and return a column for each of the functions. So this is just on the one variable. So your mean, your median are in yellow and blue, and your standard deviation is plotted in. Oh, what the heck? How long has this been going? Oh my God, that's depressing. I'm glad somebody said something. Let's see here. It's more interesting when you can see what I'm talking about. No, I'm showing this. Okay. All right. Well, Let's start from the beginning. Okay, so first example is just a simple mean of the data. So your data on your left here is the raw data, bin data is on the right. Now you do the same thing, but you're binning on X is your binning axis, and binning on the range. Now you're applying it to two variables, V1 and V2. That gives you the figure on the right. You can get a little bit more complex. So your axis is X. You're going to bin on this range, and you're interested in applying the functions to the variable V1. And now you want to calculate the mean, median, and standard deviation. So that gives you 3 columns back with the reduced data. Then you can start getting a little bit fancier, where you have 2 axes of point data that have 2, X and Y are the columns that you want to bin on. And you want to bin on the Y-axis within this range and on the X-axis within this range. And so that will return a table that you can then rearrange into an image, essentially. So this is the X and Y data. So this is why I had it, is all this ISAT data. You have to apply all these data reduction to it, and you want to apply like a MAD rejection on the data when you do the binning. And so it was just becoming a very costly operation to do. But with bin stats, it becomes quite trivial. So you're binning on X and Y here, and you're just returning the mean. But your binning doesn't have to be constant. It doesn't have to be a constant range. It can be whatever you want it to be. So here's just an example of doing the binning again, but now we don't have constant ranges when we do the binning, and so you can bin in any arbitrary way that you want. Here we're just applying the median, and then you can define your own function, pass it into bin stats, and get the returned result from there. So that functionality I use just for tons of stuff. I don't know why. There's lots of situations where I need to apply some sort of binning. So that was one of the packages that came out of this work. I will go back to sharing. That doesn't look right. Okay. The other one I also wrote was fast geoprojections. Transforming between coordinate systems can be quite expensive, especially when you're working with point data. And that was something that was kind of slowing down my workflow. So I wrote this fast geoprojections. It's very limited. It only supports kind of the most popular projections, but it's really fast. It's like 1 or 2 orders of magnitude faster than the industry standard, which is Proj. And that's thanks to the, I can't remember the package name now. I'll remember it later. And then one of the packages I wanted to give a shout out to is this least squares fit. When you have this much data, a lot of the more complicated, maybe better methods just don't work. It's just too expensive to apply them to these huge data sets. And I find myself always going back to these least squares fits, because you can quickly model the data in a way that you think is appropriate with a certain amount of smoothness to the data. And then that helps greatly with outlier rejection, with gap filling, and all of those types of things. I spent about a year with something that is much better, which is Gaussian processes, which, yes, is that a thumbs up or a question?
Well, thumbs down question. I mean, if you go back to the last slide, right? So least square fit is not fast and it is not highly effective. I'm curious why you're still making use of least squares fit, not the resolved FDL changes to this, because the least squares fit has some known issues in terms of its it has some known numerical stability issues that causes a lot of lack of convergence. I'm wondering then, like, if you're staying on this, is this because you've been using it for
No, I think I went into the modeling toolkit ecosystem and used that to start with, but it was convoluted in the way, if I remember correctly, this is like a year and a half ago, it did not seem intuitive for least squares fitting.
A year and a half ago, it didn't exist. So nonlinearsolve.jl has a least squares problem that can solve these least squares problems, and we highly recommend that because there are some corrections to the nonlinear, basically the process. Because the least squares fit has a Leavenworth Marquette method that uses the formation that uses the a times a prime, which gives you a higher condition number, and so it has a lot of convergence issues whenever you have the large eigenvalue problem. So I'm going around and basically continually telling everyone, like, we need to stop using least squares fit over and over and over and over. So I'm just kind of,
So
I want to go, we can work together doing this, and
yeah.
translate it over to nonlinear solve if it improves something or whatnot. But we can work together on seeing if we.
Yes. So when I ventured into this space, I think you got a couple messages from me, and basically it was like, okay, least squares fit is working, and I, to retool things, once it's in, you kind of stick with it for a while until there's an activation energy to change something. So maybe you'll provide just enough activation energy that I'll go.
I can work with you on it. And I think the two things here is that least squares fit has some issues working with the different automatic differentiation libraries and such, so that can limit its numerical accuracy with the Jacobian, right? And then the second thing is that it uses the Leavenworth Marquette formulation that uses the a times a prime, which doubles the condition number of the solve. And so if you have very large eigenvalues in your Jacobian, it was non-convergent.
I'm certainly not going to argue that with you, Chris.
So if you don't really, they need to see some pictures, right? I
Yeah.
still want to try to see if we can transition all the ecosystem over ASAP.
Yeah, that sounds great. But the point is not lsqfit.jl. My point is that is the operation that I am doing over and over and over and over in everything I do. I am fitting a model to everything. And I have tried to, I've looked at all sorts of different methods, Kalman filtering, Gaussian processes, and I just always end up coming back to least squares fit. It is just fundamentally such a powerful tool. And so.
And I think there might be a bit of a discoverability problem with this, right? So with nonlinear solve, we have the nonlinear problem. We also have the least squares problem baked into that package as one of the pieces. We don't have it in a separate documentation or whatnot. So I've been wondering if people have been able to find this as like, oh, this is the alternative to least squares fit or not. It seems like we haven't done very well on the discoverability aspect. I'd be happy to chat with you more about, whether we should like make a different documentation or
Yeah.
what we should do about this. Just to make it clearer that this.
Because I did go down that path, and I still remember like there were stumbling blocks along that way. Like it felt more difficult than it needed to be for what I wanted at the time. Anyway, okay, we'll continue that. That's great. Yeah. Oh. Yeah. Okay. But I'm going to plow through here because I know I'm going to run out of time. Probably have. Gaussian processes is just something I always like to advocate for, because as we can improve the computational efficiency and also come up with approximations to Gaussian processes, for earth sciences, this is the solution to every problem. It is absolutely an elegant way to relate your data without using a physical model. It's a non-parametric approach, and the things you can do with Gaussian processes it's beautiful. And then the things you can do with deep Gaussian processes is even more powerful. And so I'm hoping that we'll see more development in the Julia system with this. But Cambridge, the Turing Institute is invested in this, and they've been doing great stuff. Visualization packages, yeah.
So in the Gaussian processes, there's 3 packages that are Gaussian processes. Did you try the different ones, and can you give like an overview of what you ran into, or did you just go straight for one and you ended up working out?
Actually, I ended up partnering with Cambridge for a little bit on this, and we had a PhD student come and work on this. I explored, they've kind of merged though, because what the creator of Stano, is that right, is actually at Cambridge now and is kind of developed. They've kind of merged into one ecosystem over there. But no, I probably couldn't cover that all right now, but I'd love to talk with you about it later. Visualizations, you know, Mackie, Simon's doing amazing work with all of the Mackie stuff. GeoMackie and Shul has done incredible stuff. And then Tyler, which came out of this workshop a couple of years ago, has been invaluable to the type of work I do, because all of this you need to visualize in a spatial context. It's our XY plot. We're just always plotting our data, because it all makes sense until you plot it, and then it just looks like garbage, and you're like, oh, I clearly did something wrong. So what that resulted in was this. This is observations on the left in these 2-degree tiles, and on the right is your model. And so this is just showing how well we were able to calibrate the model. It's a bit difficult to see at this resolution, but we did a pretty good job. This is a significant advancement over the state of the art. And what you can get out of that now is kind of glacier change for all of these different regions on Earth. And I've got them plotted on the right-hand side here. The gray is Grace follow-on, so kind of these large aggregate regions, and we're comparing to what we're getting from the altimetry and photogrammetry. And so we get a detailed picture of how all of these different regions are contributing to sea level. So that's 8,500 gigatons. A gigaton is a cubic kilometer of water. So that's 8,500 cubic kilometers of water that has gone into the ocean over the last 20 years from glaciers. It's just a monstrous number. So that's just shy of the total contribution from both Greenland and Antarctica combined. Right, so these glaciers take up about 1% of the surface area relative to ice sheets, and yet they contribute a disproportionate amount of water into the ocean. And then you can take that water and you can route it through all the rivers, and then you can compare that with model estimates of river flow, and you can just take the ratio of, you know, glacier contribution versus other sources, and you do that for every month of the year, and then you pick your maximum month for glacier contribution. So you're just looking at that 1 month a year, you know, what is the maximum amount of water that could be coming just from glacier sources? And that number is quite high. And so the white in this image is fractions of between 0.8 or 1, so all of the water coming from glaciers, and then all the way down to a fraction of 0.2. So you see places, these hotspots like high mountain Asia, where there's large populations and a large amount of the water in the rivers is coming from glacier sources. Also in South America, places like Greenland and the high Arctic, you know, it doesn't matter, it just goes straight into the ocean. Nobody's dependent on that water. But here, there's a zoom in here. So Edmonton and Calgary, I did my PhD in Edmonton, so that's why I've shown it here. You know, it's kind of around 25% of the water in the lowest month would be coming from glacial sources. And then South America, you know, Santiago has a large dependence on these sources. Now, what is not included in this analysis is man-made reservoirs, right? So that will obviously affect the vulnerability to the loss of glaciers in these regions, but the idea of the analysis is just to highlight the importance in the amount of water entering streams. And then Karachi, was it 20 million people, right? And about 70% of the water comes from this one river. And that river, you know, about 40% of it is coming from glacial sources during its minimum month. And just highlighting that it's not just the water going into the ocean and contributing to sea level rise, it also matters for water resources. And so your timing of when that water will be released will change in the future as the climate changes. And then once the ice reservoirs are gone, you know, that precipitation will be there, but it won't be there in those warm months. And so you'll see a large drop in availability of water resources during those dry periods. And this last step is really just a shame and Shul, but I think he's helped fix my problem here. So we're trying to work with geometry ops to look at the population around these rivers. And so basically you can have a histogram of this many people, you know, are within X distance of a stream that is fed 50% from glacial sources. And that number is large. It's in the tens to hundreds of millions of people. And so this is just an ending slide, kind of overview of JuliaEO, like what I'm looking forward to in the coming year. You know, Raf is talking about unitful integration into rosters, which will be, or is it dimensional data or rosters? It's going to go into rosters. Yeah, okay, I've got it labeled wrong here, but that'll be huge. Tracking units is just a nightmare. Vector data cubes or DIM data sets is this idea of extending what dimensional data can currently hold and making it even more generic or able to hold different data types. That's going to be really exciting. Improvements in the alignment between geodata frames, geometry ops, I've got geodata frames, rasters, and Yax arrays. There's a lot of talk in the community about kind of this year might be a good year that those things really start to look more similar and the syntax and play nicely with each other. So that's really exciting. Improving dimensional data index performance. That's just a shout out to Raf. Ability to save tables with metadata. This is one that I hit recently, and it's so frustrating is that we can support metadata on data frames, but it doesn't save natively. So you lose all your metadata when you go to save a data frame. But it looks like that's all implemented in Aero now, and it should hopefully soon work. Writing of dimensional data, kind of been talking about that with Raf, is dimensional data is just a great way to make your writing of your code much more literate when you're working with arrays. It almost to the point where you don't really have to document your code. You can literally just read it because it's closer to plain English. But we don't have a good way of saving that data right now, and so that's a big limitation. Let's see. Oh, Earth access is how we go and get all this data. You can see all the challenges. You know, there's multiple packages about just how do we go and get the data and bring it to our computer. In Python, they have Earth access, which is making huge strides on the NASA side. It's gaining a lot of popularity, and it just does a lot of the management behind the scenes of all the routine things we have to do when we go and try and get the data. And I'm going to continue to push on them to see if we can get a Julia version of that. And then the stuff that Anshul was talking about is like just moving towards this cloud paradigm, or at least getting ready for it. So all of the major providers are moving all of their data to S3, and that's fundamentally different in how you access and work with the data. And so if Julia has the tooling ready for when all that data arrives on S3, that's going to put us in a much better position because all of the other languages are also having to develop all of this tooling because it's all so new that if we kind of lean forward into it, we can position ourselves really well. And then I just wanted to say that I'm so incredibly thankful for all of the hard work. Like as I'm using these packages, people that don't know me are helping me out and fixing bugs and adding new features and all for nothing. And it's been really enjoyable just kind of being integrated into this community, and I feel like I am standing on the shoulders of giants and benefiting greatly from it. So that's it. Chris.
I didn't want to ruin your flow again, but can you go back about 3 slides?
Yes.
Or 2,
Which?
The one that has a uniform there. Yeah, so I'm curious about the choice of uniform integration of dimensional data versus using dimensional quantum. I think that there's been a lot of issues with uniform adoption due to the fact that it has, every unit is a different type, and that fundamentally makes most use cases pretty techno stable with a lot of a lot of trade-offs there, of course. I'm kind of curious if we could discuss about, like, have you looked into the differences between the different the unit approaches to be able to discuss, see why uniform makes sense in your kind of data, and whether you think that that's a general phenomenon throughout geo use cases, or whether that is something specific.
So yeah, Raf and I were talking about this yesterday, so I'll let Raf take this one.
In the case especially that a uniform is better
Oh, okay.
called Alan Rosales, and he'd like to know which Julia library do you consider best for visualization and graphing, and which works better with JuliaEO.
I always lean towards Mackie just because it's just so customizable. And then GeoMackie now has support for all of the coordinates that we use, and so I think just kind of the Mackie ecosystem, it's worth investing a little bit of time in learning it. If you're using something like dimensional data for your data, it works with plots, but it also works with Mackie, so you can essentially just take your array, if it's dimensional data, and you can plot array, and it will add the dimensions, and it will even add a title for you all automatically. So there's a nice ecosystem growing around that.
Thank
Yeah.
you. Thank you very much.
All good? Now we can go.
Thank you, Alex. Thank you so much. Super interesting presentation. So now we have a coffee break. So for those who are online, thank you for joining today, and we'll see you tomorrow at 9 a.m. here local time. If you're here, so we have a coffee break, 20 minutes, then we have the expert hour, so just hang around and talk with network, basically. See you. Thank you. See you tomorrow. Bye-bye.